Thank you very much for having me. I'll start right up because it's kind of a packed presentation, and 45 minutes is a small time. So thank you again for having me. Thank you for joining me on the last talk. I understand that you've had a full day of conferences. I hope it was enjoyable, and I certainly hope I'll be learning you some tips and tricks today on Kotlin multi-platform. Just very quickly, a bit about me. My name is Salomon Brys, and I'm the founder of the Kodein Koders company. The Kodein Koders company is actually the very first company in Europe to be certified for Kotlin training. So what this means is we have invested a lot in Kotlin multi-platform, in Kotlin native, in Kotlin Android, in Kotlin in general, and JetBrains has worked with us to certify us for Kotlin training. So as part of the company offers trainings, and of course it also offers consulting services. The Kodein Koders company is one side of the coin. The other side of the coin is actually the Kodein framework. The Kodein framework is the first framework for Kotlin multi-platform that targets basically every target Kotlin can target. So what we aim to do is provide several high-level components, opinionated components for application development, for multi-platform application development. And these components, here are some. Our very first library, our historic library, is the Kodein DI library for dependency injection. It was actually the very first non-JetBrains library to be compatible with Kotlin native and Kotlin multi-platform. In fact, we at Kodein Koders worked in relations with JetBrains when they were first releasing Kotlin native, so we could offer the Kodein DI library first multi-platform library, not by JetBrains. And then we expanded. We just released Kodein DB, which is an embedded database for Android and iOS, a NoSQL database that basically is concurrent to SQLite, but it's a NoSQL embedded database. And then we are working on other multi-platform components to help you create applications for Android, iOS, and the web servers and everywhere Kotlin can go to. We're not here today to talk about the Kodein framework, although if you do want to know more about it, please come and see me. We're here today to talk about multi-platform Kotlin. So multi-platform Kotlin is Kotlin on Android, which is, of course, it's one of its primary target, but also on iOS, the web servers and desktop. Let's go back to the title of this talk. And first, I think I need to explain some things about this talk. And the first thing I need to explain is what is a native dependencies. And I might have mistitled this presentation. Maybe I should have titled it Using C in Kotlin, Managing Native Code in a Multi-Platform Project. The idea is native code is anything that can compile for a precise target in assembly code. So things like C, C++, and we'll see other things. You can have your own native code. You can have some other native library. Basically, it's the same process, as long as you're compatible with C. The title, Using C in Kotlin, isn't a misrepresentation. You need C and not other language. So the first question we should ask is, why C? Why not other languages such as C++, Rust, or Go? By the way, if you haven't checked out Rust, please do. It is an amazing language. But the question remains, why C? There are a lot of better or more modern programming languages out there for native platforms. And the answer is C has actually a stable ABI. C++, Rust, and Go have unstable ABI. But the good news is that they are all compatible with the C ABI. So what's an ABI? An ABI is an application binary interface. What it means is it's the same as an API, but instead of exposing REST HTTP request or other thing, it exposes native symbols. So it basically allows various native components such as shared library, binaries, and other native components to communicate between themselves. And C++, Rust, and Go have unstable ABIs, meaning that their ABI changes with time and implementation. C has a very stupid simple ABI, so that every other programming language can be compatible with C ABI. So let's take a simple function, a simple C function, something like make an addition. Okay, so it has two integers as parameter and it returns an integers. If you would write in C, by default, of course, it's compatible with its own ABI, so you wouldn't have to change anything. But if you would write this in C++ to be compatible with the C ABI, you'd have to add the extern C annotation. In Rust, you'd use the no-mangle annotation paired with the extern keyword, and in Go, you'd need the export addition comment on top of the function, and then you'd need to use C-specific types. So in this example, C.ints. So yeah, you could use any language you want that compiles to assembly level code, as long as it's compatible with the C ABI, which is basically every native programming languages out there. So why would you want to complicate your life? Because you'll see that it will complicate your life. Why would you use native code? Why not, Kotlin code, Swift code, JS code? Why do you need native code? A good reason is that you need access to a native library. For example, OpenCV, LevelDB, or FFmpeg. OpenCV is an image processing library which does a lot of image recognition. LevelDB, I know a lot about LevelDB because it's actually what CodeinDB is based on. So in fact, this entire presentation came to me because I was fighting with LevelDB to make it compatible with iOS, Android, and other platforms. And things that maybe you want to do FFmpeg, so you need video compression or what have you. And of course, it's all available via native. Maybe you have your own self-produced heavy computing native code, and maybe running in a managed environment makes it take a huge performance hit. So maybe you need to compile your own native code, or maybe you need to hide secrets into your native code, because you can't really decompile native code. It's very easy to decompile JVM or Android code. It's amazingly easy. Decompiling native code, if you try, I think you're mad. Okay, so I have a question for you. I think it's supposed to use Slido, but never mind. The question is, have you worked or played with the Kotlin multiplatform environment? I don't know how it works. Maybe. Okay, we'll see the answer later. The idea, normally I would ask you to raise your hand, but the question is, how well do you know Kotlin multiplatform? And I'm going to assume that you know Kotlin, but you don't really know Kotlin multiplatform. So I'm going to define Kotlin multiplatform for you so that it's done. Kotlin multiplatform is a Gradle, an IDE plugin that defines which sources are to be compiled with which compiler. And that's it. Kotlin multiplatform is not it's not a compiler that does everything. It's actually three very different compilers that all read Kotlin code but produce different outputs. And what we call Kotlin multiplatform, it's actually a Gradle plugin that simply looks at your project sources organization and tell, okay, this code and this code and this code is going to be compiled by this compiler. So for example, you have a common source set that is going to be compiled by all three compilers, and then each compiler will then take its own source sets, which contains JVM specific sources, native specific sources, or JavaScript specific sources. And then the intersect, and then the addition of the common source and the JVM source or the native source or the JS source is given to the corresponding compiler. So it's very important to understand that Kotlin native, Kotlin multiplatform is actually your code read thrice. One for the JVM, one for native, and one for JS. Okay, so how do we architecture a project around a native library? Let's start from the bottom. First, there's your native library. This is the native library you have compiled and you want to give it access to your application. To do that, if you're on the JVM or Android environment, you need a JNI layer. The JNI layer is the layer that makes the translation and that allows the application and the native library to talk. But this layer only works for JVM and Android. If you need Kotlin native for iOS, for example, and compile your code to Apple, iPhone, then you need another layer, the Kotlin native C-interop layer. And we'll see just in a bit how it works. And if you're doing Kotlin JS, and if you don't, please have a look because it's a very, very good abstraction to the very bad language that is JavaScript. You can also create a Kotlin JS facade that use WebAssembly. And then once you have all those three layers, you create a common interface so that each layer implements the same interface. And because it implements the same interface, then your application business code can use this interface without knowing if it's on Android and using JNI, iOS and using native, or WebAssembly and using JS. And then, of course, once you have your application business, you pack it all together, you give it to a Android or JVM developer, which creates the Android or JVM app, which inherently uses the JNI layer, an iOS or native developer that will use the Kotlin native C-interop layer, or a web or Dino programmer. By the way, Dino, created by the creator of Node, has graduated to 1.0, so if you haven't checked it out and you're still doing Node, you should. Today we're gonna focus on these layers because the talk isn't about creating a multi-platform application. There are a lot of talks and documentation around that. Today we're gonna be strictly speaking about how do we interface native codes and create an interface that's easily usable by an application business code and then consumed by an application. So the first thing you need to do is to create a common Kotlin interface. And for this example, I'm going to use a native base64 encoder and decoder. This is just for the example. This is actually a very bad application of this technology because base64 exists in all three platforms, and you should really use the platform implementation rather than getting through the trouble of porting a native implementation of native base64. So this native base64 is just as an example, but please don't do that. Find a more meaningful application. So the trick is we have a common interface and each platform will provide its own native implementation. And once each platform has provided its native implementation, then you can use it in your application. So how do we tell a platform, please provide me a implementation of native base64? Well, we use what's called an expect function. An expect function is simply a function that's expected to exist on each platform. Here we're saying, I expect the getCpp native base64 function to exist and to return a native base64 implementation, no matter the implementation. And then the first thing you should do is write tests, of course. So here are a very simple test set for this native base64 implementation. We get the base64 implementation, then we create a test that just tests whether the encoding work, and then we check if the decoding work, and then we check if the function fails as expected when we expect it to fail. So now we have the implementation, we have the test, we're ready to make each layer for each target. But before that, we need a C header. Whether you're going to implement in C, C++, Rust, Go, or what have you, you still need a C header. The C header defines the C ABI you're going to use to talk to your library. Let's have a look at this C header. First, there are two functions that define the maximum size of an encoded base64 or of a decoded base64 byte array. So why do we need these functions? We'll see that in a second. The base64 method function takes what you would expect as parameters. So this is C. The first parameter is a const char star, and the problem in C is that const char star could mean a byte array, or it could mean a string. And here, in this context, it means a byte array. And because it's not null terminated, because it's not a C string, then we need the length of this byte array. And the third parameter is a Boolean, whether we're going to encode as URL B64 or as normal B64. And C doesn't have Boolean, so it's a simple int 1 or 0. The problem with C is that, like most programming languages, it can only output one object. But what should be this object? Should it be the result? What about an error? How do we handle errors? So here, there's no standard. There are many standards, and I chose to use output parameters. It's pointers that we pass to the function and that will be filled by the function. And that's why we need the maximum len, because we are going to be managing the memory, and we are going to be responsible for allocating enough out cars. So the three parameters are the out cars that will be filled by the function and that will receive the base64. The second parameter is the maximum length, so that we're sure that we won't have a buffer overflow. And the third is a pointer to int that will be filled and that will receive the length of the cars, of the base64 cars that are filled by the function. Same goes for base64 decode, but now the parameter is actually a string because the base64 is a string. So we can assume it's null terminated, so we don't need the length, and the three output parameters are exactly the same. And the function returns a char star. It will be an error, it will be a string. If the char star isn't null, then that means something went wrong, and the description of what went wrong is in this char star. This kind of C API design is often found in Windows headers. So no matter the implementation language, as long as it compiles to all needed target, you can compile, you can use Rust, C++, Go, whatever you want, but you need to be compatible with a shared C API. So now we have everything, and we can start creating our layer. The first layer we'll create is the most created one. It's for the JVM and Android, and of course, it uses JNI. There are 4 steps when creating a layer for JNI. First, create a Kotlin interface, then create the C or C++ bridge, then bring them together with a Kotlin facade, and finally, test it, of course, test it. So part 1, create the Kotlin interface. It's very simple. The only thing we need to do is take our native base64 interface that we created earlier, implement it in a class, and just say, okay, those 2 functions are going to be external, meaning they're going to be defined in JNI. And that's the meaning of the external keyword. It means I'm not going to implement them here. I'm going to be implementing them in C or C++. So this is the easiest part. Then we need to create a C, C++ bridge. You can create it in C or in C++. I use C++, but if you're allergic to C++, you can simply use C. So first thing first, we create the function. On this example, I'm going to focus on the encode method, on the encode implementation, but the decode implementation is really the same. The first thing you need to do is find out the name of your function. Oracle used to ship with the JDK up to 8 a tool that would work with JVM bytecode that would generate those function name for you, but that tool was deprecated in favor of a tool that only works with Java source code. So how do you get the name of this function? Well, you have to infer it yourself. It's usually Java underscore the package underscore the class underscore the method. The two first parameters that this method is taking are provided by the JNI. So it's the JNI environment and a JObject that we're not going to use, which is the object that this method is being called onto. And then those two parameters are what you would expect. It's a byte array and a Boolean to know if we encode as a URL or not. Then in the method, the first thing we do is we get the array, we get the length of the byte array, we get the maximum length that we need to allocate, and then we call malloc to to allocate memory that's big enough to receive the base 64. And then we call the function, but for that we need the actual byte array that we're going to be encoding. And for that, we're going to use get primitive array critical. Now, you need to understand JNI for this stuff, but basically in JNI, you can access a byte array either critically or not critically. If you access it critically, then it means that you're not going to do blocking syscalls or threading calls or other JNI calls. So you can call critical in very specific environments, but if you can, you should, because it's more optimized. And then basically, we're simply calling the method, giving it the parameters, the in and out parameters, so that it can do its work. Then, of course, we're checking if there's an error. If there's an error, we transform the C string to a JNI string. We throw the error, and then we free the error because it was memory allocated for us. And then if there's no error, then we simply transform the resulting base 64 string back to the JVM, and we free the memory that we allocated just here. So straightforward, but there are a lot of code, of boilerplate code, to be compatible with the JNI. Then you've written your C or C++ JNI layer. You need to compile it. To that end, I like to use CMake. So this is an example CMake script that compiles this C++ JNI layer. So this is pretty classic. I just add a subdirectory for the actual base 64 implementation and add a shared library that will be compiled with the JNI code. So this is classic CMake. With that, you can compile. And that only works for the JVM. If you need to compile for Android, then you should probably use the Android Gradle plugin. So the Android Gradle plugin works by giving configuration using the Gradle plugin. It's pretty classic. The only thing you need is here to tell a CMake that you don't need all the JNI, just the parts of the JNI that Android uses. And then in the Gradle Android plugin, you need, of course, to tell it where to find your CMake. And then after that, you still need to write your Kotlin facade. What do I mean by that? We still have our class, but that's not enough. We need to load our native library, our native shared library. On Linux, it will be a SO. On macOS, it will be a dlib, a DLL on Windows. So we still need to load it. And to load it, we simply add a companion object and a constructor on this companion object. Basically, it's a static constructor that will load the shared library. The only problem with that is that on the JVM, you need to distribute or bundle the native lib for each platform with your jar. So, for example, you need a jar and the Linux shared library if you're going to run on Linux. There's no standard way to embed a shared native library on the JVM. Hopefully, Android has solved this issue with the AAR bundle format. So, Oracle, if you're listening to this, maybe there's something you're missing. And then finally, once we have all that, we can test. But we still need to tell Gradle, to tell the JVM, where is the library. So we need to configure Gradle to the Gradle test task to fetch, to add the library to its library path. And then finally, we can run the tests with Gradle. If we're using Android, there's a trick. The trick is we need to disable unit tests. We need to disable unit tests because we're going to load a shared library, and that shared library has been compiled specifically for Android, so it will not work on your computer. So you need to disable your classic unit tests that usually run on the computer itself. Then, weirdly enough, a file must exist in Android test/Java. Even if all your tests are common and there's no specific test for Android, there still need to be a file. And then you can run your connected test. And connected test means the test will run on a device. And once it runs on a device, it can load the device shared library, and then you can have the assurance that it works. Okay, we've done it for Android. Let's do it for native and iOS using Kotlin native. So 3 steps to do that. The first step is to write a C-interop file. The second is to build the Kotlin facade. And the third is, of course, to test. The first part is to write a C-interop file. It's a definition file. It's its own format. But basically, it says, OK, go read this header and generate a Kotlin native layer for me. So the good news is that you don't have to write C or C++. You don't have to write the translation and handle the memory and all that. It will be generated for you with this C-interop file. And for example, if we take the base64_c header that I've shown you earlier in C, it will generate those functions. So the first function are pretty straightforward. It's the max encoded length and max decoded length. So it takes an integer and returns an integer, nothing fancy here. The base64 encode function that's generated by the C-interop tool of Kotlin native is a bit more interesting. As we can see, the first parameter is a string. Why? Because Kotlin native have seen that the first parameter of the base64 encode C function is a const char star. And as we have seen earlier, a const char star in C can represent either a byte array or a string or null terminated string. And most of the time, it will represent a null terminated string. So when it sees a const char star as a parameter, Kotlin native is nice enough to say, okay, this is a C string, I will translate it to a Kotlin string so that you don't have to. The problem is, in that specific instance, the const char star parameter isn't a null terminated string. It's a byte array. So we need to tell Kotlin native that do not convert const char star to string on this specific function. Because on this specific function, I need to send a byte array that could or couldn't, or that may or may not contain the null byte. The rest is standard parameters. cValuesRef is just a way for Kotlin native to tell you that it's a pointer. So I'm not gonna teach you Kotlin native, but this is a way of representing pointer in and pointer out. The base64 decode function is the same, But this time we can leave the first parameter as a string, because it is a string. Base64 is a string, so Kotlin Native will transform it to a null terminated string, and that's fine. That's one more thing that we don't need to do. So once you have that, you need to compile the native part, your native library, for Kotlin Native, and it's not trivial. For example, what does it mean to compile for Linux? Because you can compile for Ubuntu, for Debian, for Red Hat, or for a lot of other distributions, and they all have their own sysroot and system and etc. So Kotlin Native comes with its own sysroot and its own compiler toolchain that you need to use when you compile. And if you're using C++11, you can't. This toolchain isn't compatible with C++11. It's an old toolchain. They need to update it. They haven't yet. So the only thing, if you absolutely need C++11, then you need to create a shared library and a static library that loads the shared library. But if you don't absolutely need C++11, then you can compile with disabling the C++ ABI for your native code. If you're compiling for macOS, it's very simple. You just have to add the macOS min version to 10.11. If you're compiling for Windows, of course, it's complicated. You're not compiling for Windows Visual Studio. You need to compile for MinGW, which is another implementation of compilers. You need to use their own compiler. You need to use the f-emulated TLS option when you compile. So yeah, you need to be aware of those things. And finally, if you're compiling for iOS, well, there's no official tool to compile for iOS, but there's outside of Xcode, I mean, but there's a very good project which is called iOS Toolchain for CMake iOS Toolchain. I don't know who's maintaining it, but bless him, because it's amazingly simple to compile a C or C++ library for iOS. You just have to inform CMake of the iOS toolchain file. So yeah, that's another thing that's taken care for us. So once Kotlin Native has generated this bridge for us, we need to use it. And to that end, we need to write a facade that will transform this low-level Kotlin Native C-interop generated code to the interface that we created earlier. And that's very simple. We memscope everything so that we're sure that there are no memory leak. And then we get the maximum len of the result. And then we allocate enough memory to fill it. Then we call the method. Then, of course, we check for an error. If there is an error, we need to free it because it's memory that was allocated for us. And then finally, we transform the result into a string. Does it ring a bell? It should. It's the exact same algorithm that we implemented using JNI. The only difference is that this time we're not implementing it using C and JNI functions. We're implementing it using Kotlin and Kotlin native function. But it's the same thing. Get the len, allocate memory, call the function, check the error, return the string. Last thing we need to do is to disable cross-compile, because Kotlin Native will cross-compile by default. And the problem is for Linux only. So if you're on macOS or Windows, it will try to compile for Linux. The problem with that is that you're not going to compile the native library for Linux when you're on macOS or Windows. So you need to disable cross-compilation, which is enabled by default. This is a very documented code that you can find on the internet. I'm not going to go into it. It's for Gradle, and you'll, of course, have access to the slide later. But you need to add this to your build Gradle KTS if you're compiling for Linux from another environment. And then, phew, we can test. You need to test on Linux. That's very simple. Just run Linux x64 test. You need to test on iOS. That's as simple. Just run Gradle W iOS x64 test. So yeah, test integration on Gradle and the Kotlin Multiplatform plugin is really well done. Finally, the third layer that we need to create is for web and deno, and that's using WebAssembly. Three parts. First part, you need to use mscriptum to compile your native code to WebAssembly. Then you need to write a Kotlin facade, and then, of course, you still need to test it. So the first type is to compile for mscriptum, and I'm going to go quickly over there because it's always CMake. Or if you're using Rust, then it's another kind of configuration file. But basically, you need to tell CMake that you're exporting for WebAssembly, and then you need to disable exception caching if you're using C++ exception, and then you need to export the function that you're going to use. So to tell the mscriptum compiler that these functions in particular are going to be useful, maybe you need standard WebAssembly mscriptum function, and then you need to tell WebAssembly where to put those files. So this is very standard CMake. If you need to compile for WebAssembly, then there's a lot of documentation out there. And then you need to write the facade because you've compiled to JS, but once you've compiled to JS, you still need to write a facade that will use the WebAssembly function and implement these method into the nice interface that we've seen earlier. So this is the function. The facade. I created a small utility function that helps me manage memory with malloc and free. So you still need to be careful of your memory. And then first we get the length. We copy the bytes that we're going to encode into WebAssembly memory. Then we allocate enough bytes. We call the function. And then we check if there's an error. If there's an error, we throw the error and we free the pointer to that error. And if there's no error, then we copy back the memory into the JS memory and we get the encoded string, base64 string. Does it ring a bell? Once again, it should. It's the same algorithm that we've written in C4J9 in Kotlin native. This time, it's still in Kotlin, but it's in Kotlin JS. And once again, it's the same facade, it's the same algorithm that we're going to use to translate from C to this interface. You may have noticed that all those native methods are on an object that here I called W. What is this object? Well, it's the compiled WebAssembly, because on JavaScript, you can't use native WebAssembly code directly. You need to load it. And on iOS and Android and JVM and native, the loading happens synchronously. But on JavaScript, the loading happens asynchronously. So you need to handle the asynchronous loading of WebAssembly, and you need to load the WASM file and check that the browser has correctly understood it. Finally, you need to test. And to test, you need to configure the testing. So first, you need to tell Webpack, because Kotlin JavaScript uses Webpack, to correctly load the JS file that was produced by mscriptum. Then you need to inform Gradle where to find this WASM file, and then you need to inform Karma, which will run the JavaScript test, where to find this WASM file. So this is a lot of configuration, but at last, finally, we can run the test, and it works. So, managing native dependency in a multi-platform project, job done, right? We've done it. We've seen how to implement this in JNI, in Kotlin Native, and in JavaScript. I have 6 minutes left, so I want to go back on what we've learned so far. There are pain points in implementing a native library and making it available to Kotlin Native. And the first pain point is pretty clear. You have to implement the same facade algorithm for each platform family. So for JVM and Android, for native and iOS, and for the web, And I'm very well aware that most of you will just target JVM Android native and iOS. WebAssembly is more for the glory of doing it. But yeah, for each platform family, you need to maintain your own manual facade. And as you've seen, there are a lot of configuration quirks. You need to configure Gradle, CMake, Karma, and a lot of things just so that your tests can load the native code and run correctly. And you need an understanding of low-level C memory and the garbage collector that you're targeting. It's very important to understand how memory works and how it is managed so that we can write these facades as efficiently and as correctly as possible, which means that you need to understand the difference between non-compatible managed memory and native memory. And that means non-trivial optimization. So let's quickly go over some examples. For example, memory copy. Every time you pass memory from the managed environment to the native environment and back, there is memory copy. For example, JNI does this with its own function. When you create a string, when you read a string, it in fact creates new memory and copy the values because it's not the same encoding, it's not the same alignment. Kotlin native does that also. When you have a byte array and you transform it to C values, it actually copies the memory into native memory. And when you have a const star and that you transform it to a Kotlin string, then it copies back from native memory to Kotlin managed memory. And of course, WebAssembly does that as well. So you need to be very aware of memory copy. It is happening. You need to know that it is happening, and you need to understand where it is happening and how you can mitigate that. Just because you can call a native function doesn't mean that it will be more optimized, because that memory copy can take time, and maybe the optimization that is running native code is actually offsetted by this memory copy. So you need to be aware of that, and you need to try to find ways to mitigate that. Memory allocation is another problem. You do that on the JNI by using in C malloc and free. You do that on Kotlin native by using memscope and allocating memory. You do that on JS, on WebAssembly when using malloc and free. So you need to be very aware of your own memory allocation, and as soon as you're targeting native code, you can have very easily memory leaks. So you need to be very aware of your memory allocations, and you need to manage them. Know that all pointers can be represented as a long in Kotlin native. So that means that if we go back to our layered to our layered architecture, I think that when you're going to interface non-trivial native code, you'll need another layer. You'll need the low-level interface layer and common facade. Let's take an example for that. Let's say you have this, an interface cursor, an interface collection, and you can create a cursor from the collection, and the cursor actually manages some memory. So you need to close the cursor when you're done with it. Okay? You can implement these interfaces in each platform, but it's complicated, and you'll have to make the same memory allocation and memory management and resource management in every layer. Or what you could do is get rid of these interface and create a collection native, and that with a simple method, create a cursor that returns a long. The long is a pointer. So now you can manage the memory in Kotlin, and you can write the memory management code just once. Then all the three methods of the cursor can go there. You know, get the value, advance the cursor to the next value, and close the value. All you have to do is pass the pointer to the methods. And from that, you can even optimize, meaning that, for example, you could have a function that returns the length of the value so that you don't have to allocate a new byte array every time. You just have one byte array, you pass it to cursor value, and the function cursor value will actually fill the byte array. But you need to know beforehand if your byte array is long enough. This allows you a non-trivial optimization by reusing always the same byte array, but instead of writing it every time in C, Kotlin Native, or Kotlin JS, you can simply write it in Kotlin Multiplatform in common code simply by stating that a pointer is long. And then, of course, you write then a simpler interface that uses before in the backend this collection native, but that exposes a nice API for the application developer. I want to leave you with some joy points because there aren't only pain points. The first joy point is that it fracking works. Isn't it amazing? It's a lot of work, but you can interface a native library for Kotlin Native, Kotlin JVM, and Kotlin JS and use it everywhere. It offers a lot of flexibility, and you can use it in a lot of settings. And finally, it's challenging. We are all developers for the journey that is developing, for the learning that is developing. And by implementing such a thing, you need to understand C, CMake, JNI, Gradle, Kotlin Native, C-interop, Mscripton, WebAssembly, and a lot of other moving parts. And being able to tell, okay, I've done it, it's quite a challenge. I'm proud of myself. And that to me, that's a real joy point. It forwards our understanding of computing. Thank you very much. Hope I have time to take questions now. And thanks again to mdevcamp for inviting me.
Hello there. Thank you very much, Salomon, for your talk. If anybody has any question, now is the time to ask them on Slido. Code is mdevcamp, and this is main stage. We have a couple more minutes before we will send Salomon to the 3D world, and you can ask him questions and discuss with him in the speaker's corner. But if you want to ask the question now is the time. I'll give it probably 10 seconds to submit your questions. We don't have any yet, Salomon. Just for you to let you know. Before we have some, I would just like to invite you for lightning talks. We will have probably 15 minutes of a break. Lightning talks will start at 5:20, which is 15 minutes from now, I believe. 16 minutes from now. They will be streamed across all of the 3 stages. So it doesn't matter if you're joining on the main stage or the desert stage or the castle stage. They will be streamed all stages. The same streaming will be everywhere. So it's totally up to you where you want to watch these if you're in the 3D world. If not, you can watch them on the website, also in any window. And after lightning talks, I would definitely like to see you all at the final words from our team. We would like to say some thanks, goodbyes, some additional information, and don't forget to join for the after party. If you haven't done so, please download the latest build of the 3D app to join the after party, so you're able to fly and enjoy other new modes our developers put in the last minute. And Salomon, we still don't have any questions here on Slido, but folks, if you want to ask Salomon some question or discussion, please join him in the 3D world in the speaker's corner. That's right next to oh, we have a question. Oh, it's not a question. It's thank you for your talk, Salomon. So, yes.
Whoever you are, thank you very much.
So thank you very much to all the viewers, to all the attendees. Salomon, thank you very much again for your talk. And now you're free to go to the 3D world to join the crowds. And everybody else, I'm going to see you in 15 minutes for the lightning talks. And thank you once again for your talk.
Thank you very much.